I want to talk today about a bunch of different hardness results, which you may have heard me talk about hardness results before, but these are all brand new results from last year. And in particular, the idea of impossible Mario levels. And by that I mean Mario levels that there's no algorithm to solve or to play optimally. You can't figure out whether this level is solvable in finite time. What I'm showing in the video here is a particular level that was thought to be unsolvable by mere humans and only be solvable by computers. It's called Trimming the Herbs. And it's a human-created level that was thought to only be possible to be executed by computer-assisted play. But after several weeks of trying, it was finally solved, and this was the last level that any human had not solved in a game called Super Mario Maker. So it was a big event, I think, last year. Anyway, we're going to talk about a more computational complexity perspective of Mario, but this is a fun, motivating example. And a brief crash course on complexity theory. You probably have heard of NP-completeness. You probably know what it means. The short version is if you have a puzzle that has a solution, there's an easy way to demonstrate that solution to somebody. You can prove that you have a solution very efficiently. A simple example is Sudoku, where you can give someone the numbers, they can check that you satisfied all the conditions, and that's nice and polynomial time. But today I also want to talk about some higher complexity classes that are less common. PSPACE completeness is like running a computer with polynomial memory, probably for exponential time. And an even harder notion that I don't usually talk about, but I get to today, is RE completeness. This is what you probably know as undecidability. But RE completeness is a particular type of undecidability that tells you that if your puzzle is solvable, you can solve it in finite time. But if it's unsolvable, you will never know. You need infinite time to detect that it's unsolvable. So that's the ultimate in hardness in our world, and that's our goal, is to get all the way to RE completeness. And of course, polynomial time is down here. That's what most of computational geometry is, and that's the good case. We're interested in these bigger classes: NP-complete, PSPACE complete, RE complete. Okay, and I'm going to talk about three main problems today. One is Tetris. I hope you've all played Tetris. It's a great game, and it's also NP-hard. And we're going to talk about NP-hardness. And we'll build our way up to ultimately Mario and undecidability of Mario. And in between, we're going to talk about another problem that comes up in a lot of pencil and paper puzzles, which is Hamiltonicity and grid graphs. This may be a problem you've used before, but we have some really cool new versions that are now NP-hard, and we didn't know that before. So let's get into Tetris. So first, here's the original game of Tetris as it was rendered on Electronica 60 in 1984, when I was 3 years old. And these are the three versions of Tetris that I played as a kid. This is the PC version, and the Game Boy version, and the Nintendo version. All three of them, I think, at some point were illegally licensed, and it's a fun topic. You can watch this movie called Tetris from 2023 if you want to learn more about that. This may be slightly accurate, but I think you understand the idea. You have tetrominoes falling from the sky. If you fill a line, it clears. And in the real world of Tetris, there's been a lot of progress just in the last year. There's this 13-year-old kid who finally beat Tetris, in the sense that the NES version of Tetris has a bug. So eventually the code overwrites itself, and if you get to a high enough level and you're a bit lucky or unlucky, the entire game crashes, and that's considered the end of the game, or kill screen. And this finally happened after 34 years. It was also conjectured that no human could do it, because along the way you have to play a level of the game where it's basically black on black, so it's almost completely invisible, in addition to being incredibly fast. And even more, just late last year, another teen used a modified version of Tetris that just removed this one bug so that you can play forever. And then if you get to level, I think, 256, you roll over back to 0, and this is the first time this has ever happened. It takes 2 hours to do, an incredible gameplay. Again, very difficult. With high probability, this isn't even possible, you can prove, but humans have achieved a lot. All right, so from our theoretical computer science perspective, we have this problem. I'm going to give you the current state of the board, or you can think of it as the initial state of the board. I'm going to give you a sequence of pieces that's going to come, a very long sequence, and you want to know, can you survive? Or can you clear the board would be even nicer. There's also versions involving score, but these turn out to be just as hard, so I won't talk about them. One of my first papers about analyzing games, 2003 was the final journal version, I think, proves that Tetris survival and clearing is NP-complete. And that reduction used a lot of rows, a lot of columns, and a lot of different piece types. At JCDCGGG in 2019, we proved that 8 columns are enough. And this is great because the regular game has 10 columns, and the super mini version you can get has 8 columns. That's the smallest version of Tetris I could find. And so our proof applies to all real Tetrises, except we need n rows for this to be hard. And I thought I'd give you a sketch of the proof and then tell you about our further improvements from last year. So like any hardness result, we're going to prove it by a reduction, and reducing from one of my favorite problems, 3-partition. I give you n integers, and they're reasonably small. They're polynomial, say between 1 and n. And so here I'm representing integers by these sticks, or little rectangles. And I'd like to group them up into triples, n over 3 triples. Here they are, such that they have the same sum. So the total height here is t. And you want to know, is this possible? It's not always possible. Deciding whether it's possible is NP-complete. So we're going to represent these numbers as sequence of pieces. And we're going to represent the target sums of length t as these buckets of height roughly t, some constant times t. We're going to have n over 3 of these buckets stacked on top of each other. This is to make it so that the number of columns is small. And here I've got one of the buckets zoomed in, and we're going to fill that with pieces. So here's what it looks like to represent a particular number ai. We're going to start with an L piece, and that's going to kind of level off the bucket. Otherwise, it's too bumpy, and you wouldn't be able to place this square. And so there's one bucket that gets initialized, and then it turns out it has to take all of these pieces that represent AI. So you're not allowed to split up AI into 2 parts because only one of the buckets will have this L. And then you fill the rest, you fill that height of AI, and then you have a couple pieces at the end so that you have the same shape that you did at the beginning. So relatively simple proof. Of course, doing the case analysis to make sure this is the only thing you can do is a bunch of work, but that's one thing. Now, this uses a bunch of different piece types. We've got an L, we've got an I, we've got a J, and we've got a square. Just for fun, here's what it looks like at the end. There's a couple columns on the right where you put in a bunch of squares, and then you put the T, and then boom, 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 we clear all the lines. Very exciting. So it also ends up clearing the board if you can survive. All right, Tetris is with tetromino pieces, 4 squares. You can also think about trominos or dominoes or monominos. We have another paper about these different cases. Kind of highlight one of the most interesting things is that some of these problems are open. Like, can you survive with trominos? We don't know whether that's NP-hard or polynomial. With dominoes, with rotation, we don't know. It seems like they should be easy because it's related to matching, but we don't know. Actually, without rotation, dominoes are hard to clear, at least. So fun stuff. And I guess also interesting is, well, I just showed you k equals 4, hardness proof. You can solve all larger k with a generalized proof and solve all. It's not like with 100 ominoes it becomes easier. But our latest result is about Tetris with just 2 piece types. It turns out with any 2 piece types, pick your favorite 2 tetrominos, could even be L's and J's, which are reflections of each other. Tetris clearing, at least, is NP-hard. And in some cases, we can also solve some other open problems. It's NP-hard when you just have hard drops. Hard drops are when you move the piece at the top, maybe rotate it, and then drop it all the way to the bottom. No last-minute twiddles, which is usually there's a button in Tetris that drops the piece from top, and you get more points if you do that. There's also a variation of Tetris which has infinite gravity. In the Tetris world, it's usually called 20G because the height of Tetris is normally 20. And so that means that at the very beginning, your piece starts on the ground or at like maximally down. And so you're very limited in how you can move it and rotate it because you can't go back up. And so some of our proofs also apply in that case. Still open is the single piece case, although we're working on hardness proofs for that too. So let me show you how these proofs work. They're quite different and more common for Tetris clearing. So instead of having buckets, we're going to have bottles. Like this is a real life bottle, but it's going to have a neck that's more narrow and a little different from the rest of the bottle. And so now instead of the bottom of the bottle is going to be very simple. But what we're going to do is block off all but one of the bottles with some pieces. So we're going to give you n/3 minus 1 pieces that will force you to block off all bottles except for one. You get to choose which one. And then we're going to give you the pieces that represent AI, and they have to go in the one unblocked off bottle. And then we're going to block off that last bottle, and then those lines will all clear because they're completely filled. So, and then we'll continue. And this is a different way to force you to put all of the AI pieces into one bottle. So let's see this in action for two piece types, the I and the L. So we're going to first give you a bunch of L's. That's going to force you to block off all but one of the bottles. Then we give you AI different I's. And then we give you one more L and clear those top rows. And now repeat. And this works for I plus any other shape relatively easily. You just build a kind of lock at the top. So those are some easy NP hardness results. If you want to do infinite gravity, here's just an illustration of what infinite gravity looks like in real life. The piece starts on the floor, and you have, every time you do a rotation or a move, you gain another fraction of a second. And so you have time to move around, but you're very limited in how you're able to move around. And most of these proofs do not work in that regime because once you fall into a bucket, you can't get back out. And so in this case, here's one example where you give a lot of squares. Now squares are too fat to fit down one of these columns, and so you're able to place them, if you place them in the right order, you're able to place all of those except for one. Then you get an I, you can put those in the one place that they fit, and then you get one more square and clear it out. And then eventually you fill everything. You have to check that all of these moves are possible. You clear out the last column. And then we were left with, I think, this structure down here. And with a little more work, you can clear out the rest. So that's what infinite gravity looks like. Now, for our other pairs of pieces, we need to exploit a little more about how real Tetris rotation works. You may have in your head a model of how pieces rotate, but it's actually been a matter of some debate before 2001 when the super rotation system, SRS, was introduced, and now all Tetris games follow this system. If all standard Tetris games, it's part of the definition of Tetris, the official rule set. And the basic idea is very simple. If every time you have a piece, it has a rotation center. And so when you rotate, for example, if we rotate clockwise, we get this gray outline, which is also drawn here, and so on. Okay, the interesting part is, what if some of these squares already have obstacles in them? Then obviously you can't do that rotation. And there's a series of kicks that the Tetris game will let you do. So the first one is here. You try moving that gray shape left one, so it's like here. And then if those are empty, you'll go there. And then you'll try this other kick where you go left one and up one. And if that works, you'll go there. And then you'll go down two and no horizontal motion, and so on. Actually, there's just one more test, which is left one and down two. And if any of those work, you go there, otherwise you fail. And that's for this particular orientation of the S tetromino. For each orientation, there's a different set of tests. And then for each Tetris piece, actually most of them are the same as the S. I think there's only one other piece that behaves differently. And so you can use that to great effect in real life. For example, here, if the gray is obstacles and you have your green piece, you can do a clockwise rotation and your piece will jump here, which is kind of wild. And you see some other examples of neat things you can do. And I think our paper is the first to actually exploit the super rotation system. We needed it at least to do some of our reductions. And I have here all of the reductions that we did animated. And luckily, one of our authors was able to play Tetris well enough in order to actually execute these live and record them. And I don't know, one of my favorites is maybe this one down here. The L's do some really crazy dances in order to get through these weird cavities. Navigations you may not think are possible. But this gives you a flavor of all of our proofs. I'm obviously not going to talk about every pair of shapes, but it was a lot of fun to work these all out. It may be possible to prove these hard without the super rotation system, but that's how real Tetris works, so it seems fine. Okay, so the next thing we might hope for after NP completeness is to preserve the number of solutions. And there's this very strong notion of ASP completeness, which is particularly nice. So here is a little definition, in case you're not familiar. Problems ASP hard if there's a parsimonious reduction from 3-sat, meaning the number of solutions is the same before and after the reduction. And this is sort of the best, this is a nice, stronger version of NP hardness. It implies NP hardness. It implies this another solution problem is hard. If I give you, say, one solution to your problem or 5 solutions to your Tetris game, whatever, it's NP hard to find out whether there's another. Also, it's sharp P hard to count the solutions. This is an even harder complexity class for a harder problem, which is counting the number of solutions. Sharp P hardness is a little bit easier to get, so let me tell you a little bit about that. We're going to reduce from 3-partition with distinct integers. So this is exactly the 3-partition problem before, but I added this word distinct, so all the integers have to be different. In particular, this is not valid because I have 3 pieces that are the same. So even if you forbid identical pieces like that, it was known to be NP hard, and we proved that it's ASP complete. So that's convenient, because when we have 2 AIs that are the same, you could swap them, and it would look exactly this. You'd get the same results, and that will not preserve the number of solutions, because you can permute the AIs. And so, for example, for all of these proofs, we haven't completely gotten parsimony, but we've gotten a consistent blow up in the number of solutions by n over 3 factorial, because each time you decide which columns to block off, you can do them in any order. Sorry, actually, that's this one, n over 3 minus 1 factorial. You do that n times. And then also, you can permute the different buckets, like where your triples go. So this is enough for sharp P hardness, but we really wanted ASP hardness. For this, we need a slightly harder version of 3-partition, where now my numbers are grouped into 3 types, A, B, and C, or 3 colors. You can see the colors here, it's A, B, and C. And now I want exactly 1A and exactly 1B and exactly 1C in my triples. And in that case, again, this problem was known to be NP hard, but we proved that it's ASP complete. This is useful because now you know every triple has an A, so you can decide, well, let's just put this AI in a particular bucket. We can assign those ahead of time, and they're all distinct, so that will uniquely determine which triple goes where. And we've now factored out which triples go where, and that cuts down the number of solutions to be unique. All right, so in that case, we can prove ASP hardness for Tetris with these 3 pieces, I, T, and L. As I said, we're going to pre-fill the AIs, and then we're going to follow a proof kind of similar to the very first proof I showed you, where initially the bottom of the bucket is a weird shape, and you have to put the I in to enable the other pieces to come. And then it turns out each of these piece moves, or where you place each piece, is uniquely determined. And so you end up solving you end up preserving the number of solutions. Okay, so that was Tetris. And I will move on to Hamiltonicity and grid graphs, another NP hardness problem. And this is a pretty famous problem. It's used in a lot of reductions. You're given a grid graph. This is the original proof from 1982 when I was 1 year old. You're given a grid graph, meaning a bunch of dots on the square grid. And whenever two dots are a unit distance apart, you connect them via an edge. So I didn't draw all the edges here because this is actually the Hamiltonian cycle solution, but all of these guys are edges. And you want to find a Hamiltonian cycle in that grid graph. And so that's known to be NP-hard. It's used to prove lots of pencil and paper games NP-hard. For example, this is a Slitherlink hardness proof that's essentially a reduction from Hamiltonicity and grid graphs. Relatively simple. You have this little box that simulates one of those vertices, and you can add some zeros to block off connections you don't want. So that corresponds to essentially this box. It's an undirected graph, and it's what we call an induced subgraph of the grid, meaning whenever two vertices are unit distance apart, you must include the edge. And it's also known that this version with max degree 3 is NP-hard. So you don't need degree 4 vertices. And so that was known to be NP-hard. We proved that it's ASP-hard. So that's a little bit stronger. Now we have parsimonious reductions, which is useful for proving lots of pencil and paper games ASP-hard, which is useful. I mean, it's a negative result, but it's relevant when you're trying to design a puzzle. Usually you design a puzzle with a solution and you want to know, are there any other solutions? And ASP hardness tells you you're not going to figure that out. It's NP-hard to do so. Okay, but we also have lots of new versions of Hamiltonicity and grid graphs that are NP-hard and ASP-hard. For example, if you add directions on the edges, that's also hard. Okay, that's not so surprising. That's probably harder. You might intuitively think that it's harder. But instead of induced subgraphs, we can replace it with spanning subgraphs. So now every vertex in your m by n rectangle must be included, but you get to omit some of the edges. So in this example, I've cut out some edges. And so I should clarify, there's gray edges here and purple edges, or light and dark edges. And all of those edges are in the graph, and purple is showing a solution. That's a Hamiltonian cycle. Okay, so now you have almost the entire filled rectangle, and you want to know, can I find a Hamiltonian cycle? That is ASP complete. Whereas we know from the original 1982 paper, if you have all the edges in a rectangle, that is easy. It's just a parity condition. Okay, you can do the same in the directed case, but even cooler, you can take the entire rectangular grid graph, all vertices, all edges in an m by n rectangle, but each edge you give it a direction. That problem is also ASP complete. So now you've got a bunch of new versions of Hamiltonicity and grid graphs to reduce from. Please use them. I will tell you a little bit about how we obtain these results. It uses another fun problem called tree residue vertex breaking, or TRVB, from several years ago. So here's another nice problem that's NP-hard. You're given a graph, and the white vertices are called breakable, meaning you can replace a degree D vertex over here with D vertices of degree 1 over here. And you get to choose for each white vertex whether to do that or not, whether to break it. And the resulting graph should be a tree. You want to break all the cycles, but you have to keep the graph connected. So those are two tricky constraints to do together, and it turns out it's NP-hard to decide whether you can. And many versions of this are known to be NP-hard. For example, planar graphs with degree 4 breakable vertices only is enough. This is an example where we didn't actually quite solve it. There's a separate connected component over here. I think this instance maybe is not solvable. Okay, and another useful way to think about this problem is a kind of Euler tour. If I double all of the edges, so I took my old graph, I doubled all the edges, now at each vertex I get to choose, do I connect the things in this pattern or do I connect them in this pattern? This is what we call, in modern terms, a Kiki Euler tour, like very sharp angles is the idea. Every time you come into a vertex with your Euler tour, you must take either the clockwise next or the counterclockwise next edge to leave that vertex. So there's really only two choices at each vertex, how you connect things, and this turns out to be NP-hard, deciding whether there's such a tour. So we knew NP completeness, but the new result is some versions of TRVB are ASP complete. Actually, conveniently, at JCDCGGG2019, when we were analyzing some edge matching puzzles, we proved a particular version of Hamiltonian cycle to be ASP complete, just because we wanted jigsaw puzzles to be ASP complete. And that version turned out to be exactly what we used back in 2018. I guess that's only a year prior, but it felt like a long time. And then just last year we realized, hey, we can plug these together, and boom, we've got some versions of TRVB are ASP complete. So that was nice. And the version that this works for is when you have degree 4 breakable and degree 4 unbreakable. With a couple of other new simple reductions, you can get degree 4 breakable plus degree 1 unbreakable, or just degree 6 breakable. So a few different degrees you might need to simulate, but then you get perfect parsimony. So let me show you the high-level idea of how these reductions work is to just build one of these breakable TRVB vertices like so. So we're going to initially have all directed edges. And the idea is that in this loop, you can either take the even edges or the odd edges. And everything else is forced. And so this is exactly the two types of connections that we had in TRVB. But of course, we've got lots of holes here, and we want to get rid of those. So we're actually going to use a slightly different gadget. This is a degree 4 breakable vertex, and it's nicely aligned. All of the holes now will be these 2x2 grids of dots, so we'll be able to fill them. We've also added some light gray edges. I don't know if you can see those. And they are, you can prove that they're never useful. And so we still have the original forced edges. But sometimes we need them to go one way on one side and another way on the other side, and there's a little gadget that lets you flip between them pointing up and down. And we can also build a degree 1 unbreakable vertex relatively easily just by terminating the loop. Okay, so this is the basic structure. Now we're going to fill in the holes with this little gadget that whenever we have a 2x2 square of empty space, we can add a little detour to that portion of the tour and show that this doesn't add anything else. We can even add these little gray edges, and because they all point into the cycle, they're never useful because you can't escape. So this ends up preserving all of the Hamiltonian cycles, even the number of solutions, but we get a fully filled grid. So at this point, every edge, every vertex is there, and the edges are directed. If we want instead max degree 3, we can just remove all the gray edges, and boom, we're max degree 3. Or if we want undirected, actually this graph doesn't matter whether you have the directions on the edges or not. They're basically forced. Once you get started, you have to continue according to our orientation. So here we have undirected max degree 3, and there we've just proved those 3 versions are hard. For the other 2 versions, there's just a couple other gadgets. These are quite a bit easier because we don't need to fill everything. But instead we get an induced grid graph. Cool. So now, what is this useful for? We can apply these grid graph Hamiltonicity ASP hardness results to analyze a bunch of pencil and paper games. So, and this is using a technique that was introduced by Tang a few years ago. For NP hardness, we get ASP hardness and some even stronger versions, where all we need to do is build one gadget that represents a T shape, as long as we can rotate that gadget. So we have like different rotations of it here. And whenever 2 T's are connected like this, that's a valid connection between those T's. And then the goal of your puzzle should be to find a cycle that hits every T exactly once. So something like this green path. Okay, so as long as you can build a local T that behaves like that, where you can turn right, turn left, or go straight, then there's even some special versions you can use, then this will give you ASP hardness, essentially by simulating the Hamiltonicity in by using this result, depending if you're directed. So we're allowed to remove some edges here because we're only simulating T's, not four-way junctions. Okay, so here's an example puzzle. This is, I believe, a Niccoli puzzle called Mid-Loop. You're given a square grid, and you're given some dots in the centers of cells or edges, and you want to find a path that visits all of those dots. So I haven't completed the puzzle yet. It's got to be one complete cycle. But this is going to end up simulating this T-junction because all the green edges I've drawn so far are actually forced locally. And so in particular, it's impossible to leave off this top boundary because of all those edges in the way. And then you just check all the different ways to connect things. At this point, you can turn right if you use this solution. You can go straight if you use this solution. And you can turn left if you use this solution. And so that is a valid T metacell, and that proves ASB completeness of that game. You can similarly build T metacells for all of these different Niccoli and other pencil and paper puzzles. In all, we analyzed 37 pencil and paper puzzles that are all based on the idea of making a cycle that visits a bunch of things. For 16 of them, we get NP hardness for the first time. And for the other 21, where NP hardness was known, we get ASP hardness for the first time. And in 7 of the cases, actually, the old proof was parsimonious. We just now have the infrastructure to prove parsimony all the way through. And in the others, we needed a different reduction. So quite a useful framework. Already 37 puzzles have been analyzed with it, all in this one paper. Okay, and then my last topic is Mario and some friends. And now we're finally going to get to undecidability. But first, a reminder of some known results about Super Mario Brothers. I'm wearing my Super Mario Brothers t-shirt here. In 2016, so almost 10 years ago, we proved PSPACE. I wrote completeness here, but actually I mean hardness. We don't know. Well, that's the point. Is this problem actually in PSPACE? I don't know. We'll get back to that. But you can prove PSPACE hardness by building this one gadget, which is called a door. It has a particular way to try to traverse the door, which is only possible if this enemy is on the right side, not on the left side. If it's on the left side, like here, you won't be able to do this traversal without dying. And then there's a different set of traversals that are possible that will close the door, meaning they force the enemy on the left side, or if you come in here, you can open the door. So that's a useful gadget, and it turns out it's enough to prove PSPACE hardness by this other paper, which came a bit later, showing that even if you have a planar connection of these door gadgets, like a planar graph of these door gadgets, deciding whether you can get from point A to point B is PSPACE complete. So that one gadget is enough for PSPACE hardness. Now, this paper only analyzed Super Mario Bros. 1, and I've always wondered, what about the other Super Mario Bros. Games? And I'm now happy to report that we have solved all 2D Super Mario games that have been released so far. Maybe next year there'll be another one. And all of them are PSPACE hard. And these are some of all those proofs use door gadgets. So here are a bunch of them. Some of them are very similar to the ones I showed you. Some are a little different. I want to show you for fun the most complicated one, which is for Super Mario Bros. 2. This is a game, I'm not even sure it was released in Japan for a while, but in the US it was the direct sequel of Super Mario Bros. I don't think it was originally a Super Mario Bros. Game. It was completely different, and then they rebranded to Super Mario because Mario was so popular. And it's a completely different game. I mean, it's a platforming game, but very different mechanics. And so it needed a very different proof. And the idea is there's this Birdo character that shoots eggs to the left. And we're going to use those to traverse, to like jump onto the egg and jump up. That will only be possible if the eggs make it all the way to the left. But if this guy is in that location, that little mushroom piece, it's basically a movable block, then the door will be closed. You won't be able to do that traversal. So let's watch that in action. So here is a a hacked version of Super Mario Bros. 2 to run this level. You can see we jumped on the egg, and then we're going to do a bunch of different traversals. We have to drop this mushroom at a particular spot so that we can jump up through that little place, and that forces you to close the door. And finally, we'll show opening the door, which is if you come in down here. First, we move the mushroom over, which kind of locks us in, and then with very careful timing, we're going to pick up this mushroom and land on the egg, jump around, and then we can place it in the place that we want, go back out the way we came, and then we are done. So it works after much trial and error. Okay, but are these problems in PSPACE? Turns out no, at least some of them are not in PSPACE. And we're going to use a different framework to prove RE completeness. Remember, this implies undecidability. It's pretty much the worst thing that can happen. And instead of door gadgets, which had two states, open and closed, we're going to use a different thing, a new idea called counter gadgets. These have one state for every natural number, so infinitely many states, but only countably many states. And the zero state is going to be special compared to all the non-zero states. In every state, you can traverse a particular path and increment to the next state. So if you're 0, you become 1. If you're 1, you become 2. 2, you become 3. You can go all the way up to infinity and beyond. No, just up to infinity. And if we have another path, which is called decrement if non-zero, you can follow this if you're in state 1, then you'll go to state 0, but it's not allowed in state 0 because you can't go below 0. And finally, there's a third path, which is pass if 0. So this is only open in the 0 state. In all the other states, you can't do it. And with some work, you can build a universal Turing machine in this model. And it builds on an idea called counter machines. We can do it even with planar connections between these counter gadgets. So if you can build this one gadget, you get RE completeness, you get that your problem is undecidable. So we're going to do that. We can do it for 1, 2, 3, 4, 5, 6 different Super Mario games. So not all of them yet. But there's this series called New Super Mario Brothers, which most modern Mario Brothers follow this engine. There have been 4 games that are directly in that series. And another series I've mentioned, Super Mario Maker, there's 2 versions of it. All of these we can build these counter gadgets, which proves RE completeness. So I'll show you some of them. In the New Super Mario Bros. Series, it has this very general way of programming levels where if you go to a particular position, it ends up creating or destroying certain blocks. And that's very flexible. And we can use that to build a counter by... there's also these tubes that keep generating new monsters infinitely, at least in theory. In some versions of Super Mario Brothers, they really can go on to infinity until the machine runs out of memory. We're, of course, allowing a machine to have infinite memory. And we can use the number of mushrooms that are at this position to represent the counter. And whenever we do an increment, we end up opening these doors just long enough that one mushroom can make it through, incrementing the counter. If we want to decrement the counter, we open these just long enough that one mushroom can make it out into this garbage area. And so the number of mushrooms here gives us our answer, and then we can make, if there's any mushroom here, we can make it close this door, and so then you won't be able to pass unless the counter is currently 0. So actually relatively easy. And so easy, we built an entire universal machine. This is called U32. It's a counter machine that has, I think, 3 registers, 3 counters, maybe a few more. Yeah, you see all the counters over here. It's 1, 2, 3, 4, 5, 6, 7, 8 counters. And you can see Mario running around, maybe you can see, and he's triggering various events, and sometimes these mushrooms appear or disappear, or get pushed to the left or pushed to the right. Here you can see one that got decremented, and this guy just got decremented. And via enough traversal, it's very hard to imagine what computation is going on here. If you succeed, like here, Mario's able to pass here because the particular counter was 0, then you complete the level. But deciding whether you can do that in general is impossible. There's no finite algorithm. So pretty cool. You can build this in one real level of Super Mario Bros. Wii. Maybe in the other games too, but this is the one that we successfully did. It's small enough to fit in one level screen. For Super Mario Maker, we have much more complicated gadgets. I'll just go through these briefly. This is incrementing the counter. We get one mushroom up here, and it's designed only one can come in, and then he ends up on this conveyor belt. That represents our counter. If our counter is bigger than one, we can extract one in this way. This will decrement the counter. Only if the counter was non-zero will we be able to do that, and then we'll be able to make this long jump here. If there's a mushroom there, we survive, otherwise we die. And finally, if your counter, to check whether the counter is 0, we start here. And if the counter is non-zero, we can't make it, we'll die. But if the counter is 0, we would have been able to traverse there. Okay, that was Super Mario Maker 1. With Mario Maker 2, unfortunately, everything behaved slightly differently, and we came up with a completely different proof. This is passing when 0, so you're able to get through here if there are no monsters right in this area on that little conveyor belt, or conveyor that goes up and down. Let's do an increment. So there's some stuff here to force timing. That shell hits an on button, which causes the mushroom to go over on the left. Great, we incremented the number of mushrooms on the space. And if that number of mushrooms is non-zero, here it's I think 2, and we're gonna bounce one of them onto this little clown car. We use the clown car because it can only take one mushroom at a time. We only want to decrement by 1. And so the mushroom comes up here, and only then can we make that jump, otherwise we would die. And yeah, otherwise we get stuck, basically. Okay, and unfortunately, Super Mario Maker wanted to have like 4 or 5 different variations on the style of level, and there's this one called 3D Style, which is based on other 3D Super Mario Maker games, and here, Mario behaves completely differently. It's like a whole other game, and for that version, we needed yet another reduction, and maybe you're getting tired of these reductions, but this is like a whole new world of building counter machine gadgets. I think that was traversing when the counter was 0. That's a weird jump that Mario can do now. It turns on a particular timer, which causes an increment to happen. I think most fun in this reduction is the decrement. So there's this guy over here who's constantly throwing snowballs. And when we hit the blue P switch, it's going to give him just enough time to throw one snowball, and it kills one of these Koopas on the bottom, and the other ones don't make it. And great, we decremented our counter, and then traversal is through here, and if there's any monsters, we of course can't make it. Okay, so that was a bunch of undecidability proofs for Super Mario. Exciting new impossibility. Briefly, I wanted to mention some other undecidable games. Actually, the first hardness proof that used the idea of counter machines was this proof by Linus Hamilton, a former MIT student, in 2014. Before I even met him, he wrote this paper about Braid, which is a great indie platforming game. It mostly involves time travel, but this reduction doesn't involve time travel at all. It just built a counter machine using the fact that there are these devices that infinitely generate enemies. So you can stack a whole bunch of enemies all in the same spot. And he gave a more involved proof that it combined a bunch of gadgets in a particular way to simulate a Turing machine, I believe. And we observed that actually we can use this counter gadget framework and give a one gadget proof. So here we've combined a bunch of his gadgets into one big gadget, and turns out it is exactly a slightly different counter gadget. You can increment at any time, and you can decrement at any time, but you go to a different position if you were 0 than if you were non-zero. And so that's kind of cool. This seems like a new framework that might give you lots of undecidability results whenever you can generate infinite enemies. Another counter machine hardness result, this is by Zach Abel and Della Henderson, one former student of mine and one current student of mine, is for this other great game called Baba Is You. You should all play it, although it's quite challenging. It's hard to see exactly what's going on here, but there's a big stack of items, and that the number of each item gives you all the different counter values. This is a game where you can program different rules, and together they give you this behavior where the user doesn't even have to, the player can't do anything, the machine just runs. And one more undecidability result. This is a previous one that we did back in 2020. This is before counter machines. And not all proofs seem to use counter machines. This is a different kind of undecidability using the post-correspondence problem, which I won't get into here. But this game seems a little difficult to build counters, actually, because it's based on essentially when you jump into one of these chests, you instantiate a new room, kind of like a function call. And the whole video game was designed around the idea of recursive functions. And it's much harder to build counters in that world, but it was possible to build post-correspondence problem. So, undecidability is the new frontier of hardness. If you want to see the previous frontier of hardness, this class doesn't talk much about undecidability, just a little bit, but it talks all about NP hardness, PSPACE hardness, and it has new content on gadgets. If you watched a previous version, back in fall 23, we added a couple new lectures about gadgets and other planar problems. There's also a new book that's coming out this year or next year with MIT Press, but the full text is available online for free, so you can read that. It's based on the class. Yeah, that was my Impossible Mario levels and other hard games.